how do you teach a machine to think? It's a question we're all kind of obsessed with today, right? But what's amazing is it is not a new question at all. In fact, over 70 years ago, a pioneer named Grace Hopper laid out the entire blueprint in a groundbreaking 1952 paper. So today, we're going to dive into her original work and see exactly how the very first computers were taught to learn. To really get where we are now, you have to see where it all started. And in 1952, this was it. This is a diagram from Grace Hopper herself, showing how you'd solve a problem. And I want you to notice what's right smack in the middle of this thing. It's not a machine. The central processor, the part doing all the real heavy lifting, was the mathematician's brain. All right, so let's start there. Before we had anything that looked like software, there was this very clear partnership, a division of labor, between the human and the machine. I mean, think about it. The computer was basically just a glorified, super-fast calculator. Its job was to do the math. Add, subtract, multiply, divide. That's it. The human, the mathematician, had to do everything else. The logic, the order of operations, the formulas, looking up values in tables. They had to map out the entire problem step by painful step. So you can imagine this was incredibly slow and, of course, super prone to human error. So the first major leap forward was all about taking some of that burden off the human brain and finally handing it over to the machine. And this next diagram from Hopper, wow, it just perfectly shows that first big shift. The mathematician is still in charge, but their role has changed. See that? They're now a programmer. They write out a set of instructions, a program, and feed that into the UNIVAC computer. Now the machine handles what she called the arithmetical chore. This freed up the human to think at a higher level. This was a huge step for sure, but it created a whole new headache. As Grace Hopper so perfectly put it, the initial thrill of inventing these programs pretty quickly turned into the dull labor of writing and checking them. Programmers were still writing out every single instruction, line by line. It was tedious, it was repetitive, and it was a total bottleneck. Something had to change. Okay, so this next part, this is where things get truly revolutionary. Hopper realized, wait a minute, instead of making the programmer do all this repetitive work, why can't we teach the computer to do it? You could give it a library. So take a look at this diagram. It's a little more complex, but the idea behind it is just beautiful. The programmer isn't writing the whole program from scratch anymore. No. Instead, they just provide some high-level information. And now, the computer itself, guided by something called a compiling routine, goes into its own library of subroutines, pulls out the pieces it needs, and automatically puts the final program together. So what is a subroutine? Well, the best way to think about it is like a single, perfect chapter in a textbook. It's a self-contained chunk of knowledge, a block of code that does one specific thing, like calculating a square root. It's already been written, it's been tested, you know it works, you can just grab it off the shelf whenever you need it. And that compiling routine, what we would just call a compiler today, well, that's the master librarian. It's a program that runs other programs. It understands what the programmer is asking for, it knows exactly what's in that library, and it acts like this amazing automated assistant, stitching all those pre-written subroutines together to build a complete working program for you. So what does this actually mean in practice? Well, the difference was just night and day. You went from weeks, sometimes months, of tedious manual coding to just a few hours of assembly. The chance of a human making a simple typo that breaks everything, it plummeted, because you were using these reliable, pre-tested blocks of code. You weren't reinventing the wheel every single time. You were standing on the shoulders of giants, building on this growing library of knowledge. But Hopper wasn't done, not by a long shot. Assembling programs was a huge deal, sure, but she was already asking, what's next? Could the computer be more than just an assembler of parts? Could it move from just following instructions to actually generating new instructions? Could it take one piece of information and use it to create something totally new, all on its own? And the answer, amazingly, was yes. This is what Hopper called a type B compiling routine. And this right here, this is the moment the computer starts doing real intellectual labor. You could give it a mathematical function, and the compiler itself could figure out the formulas for its derivatives. I mean, think about that. The machine isn't just following a recipe anymore. It's creating part of the recipe itself. In a way, it was starting to think. This is what led Grace Hopper to write one of the most incredible, mind-blowing sentences in the history of computer science. She described the UNIVAC not as a tool, but as a student. A student with the math skills of a college sophomore, but it never forgets, and it never makes a mistake. The machine wasn't just a tool anymore. It was a student, and it was learning. And here's the thing that just gets me every time I think about this. These ideas, laid out on paper over 70 years ago, they aren't just historical footnotes. They are the absolute bedrock of everything we do with computers today. Every single time a developer sits down to write code, they're using a compiler, Hopper's compiler. Every modern programming language, from Python to JavaScript, relies on these vast libraries of reusable code. The whole idea of abstraction, hiding the messy details so the programmer can think about the big picture, it's right there in her diagrams. She was imagining a world of automated programming back in 1952, and we are literally living in it. So really, it all comes down to this. Grace Hopper and her team gave those first computers a foundational education. They taught them how to assemble knowledge and even how to generate new ideas from old ones. And that foundation built our entire digital world. So the critical question we have to ask ourselves now is, with tools that Hopper could have only dreamed of, what are we teaching our computers today?